We've spent 3 videos deriving the equations of fluid flow, mass, momentum, energy. But there's a catch. A computer can't do calculus. It can't take a derivative or a gradient. It can only add, subtract, and multiply. So, how does it actually solve them? That's what this video is about, turning the math into arithmetic. Here's the plan. We want to see how a computer actually turns equations like these into something it can solve. We'll do it with the simplest member of the family, the heat equation, as our worked example, because everything we learn here carries straight over to the others. We build it in one dimension first, where you can watch every cell update, then solve real 2- and 3-dimensional problems, and finally see where it breaks. Here's the key idea, and it's the exact opposite of what we did before. Every derivation shrank the cube down to a point, delta x going to 0, to make a derivative. The computer can't do that. So it does the reverse. It keeps the cells a real finite size and turns each derivative back into plain arithmetic on those cells. Start in one dimension, chop the rod into a row of cells, and store just one temperature in each, T0, T1, T2, and so on. That's the whole state, a list of numbers. Now, a derivative. The rate of change of temperature between two neighboring cells is just their difference, divided by the spacing. No limit, no calculus, a subtraction. The heat equation needs the second derivative, the curvature. That's the difference of the differences, the cell to the right plus the cell to the left minus twice the middle one over the spacing squared. This little pattern of cells the formula reads has a name. It's called a stencil. Put it into the heat equation and you get this. Each cell's new temperature is its old value, plus a little bit of that 3-cell difference. One line of arithmetic, repeated for every cell, every time step, and that is a solver. Let's solve a real one-dimensional problem. Start with the hot spot in the middle of the rod, shown along the top. Apply that rule over and over, and watch. The heat spreads to the neighbors, the rod cools, and its temperature profile flattens out. This is real solver output. Every frame is the rule, applied again. 2 dimensions is the same idea with one more direction. Each cell now has 4 neighbors instead of 2, up, down, left, right. So the stencil has 5 points. The rule barely changes. Now let's solve a real 2-dimensional problem. A hot patch on a cold plate. Same update rule, run on a grid. The heat diffuses outward and cools. This is what a CFD solver does, just with more cells and more equations. And 3 dimensions is the same idea one more time. Now each cell has 6 neighbors, left and right, up and down, front and back, so it's a 7-point stencil. The rule barely changes. And the very same idea works in 3 dimensions. Here's a real 3D solve. A hot blob inside a cube built from the same colored cells as the flat plate. The hot core glows and spreads outward through the whole cube as it diffuses. Same update rule, now on a 3D grid. One catch. If you make the time step too big, the scheme doesn't just get inaccurate, it explodes. Wash the rod instead of smoothing out, the temperature erupts. Hot, cold, a zigzag that doubles every step. There's a speed limit. That coefficient, the conductivity times the time step over the spacing squared, has to stay below 1/2 in one dimension and stricter in higher ones. Step past it and the solution blows up. So that's discretization. Keep the cells finite, turn each derivative into a difference between cells, and the heat equation becomes one rule you repeat in 1, 2, or 3 dimensions as long as you respect the stability limit. And here's the real point. This very same recipe is how a computer solves every equation in CFD, not just heat. Next time, we let the fluid carry the heat as well, convection, and that opens the door to the Reynolds number. See you in the next one.